Right, greetings. So welcome to today's session. From today's class, we will start looking at vertical dynamics. So here we will be looking at the uh, response of the vehicle suspension system, right? So, and then like various phenomena associated with the same. So let me briefly introduce what we are going to learn, and then like we will essentially also go further into related concepts. Okay, so when we talk about vertical dynamics, by and large, we are essentially going to look at the response of the suspension system, the vehicle suspension, and typically we are interested in looking at ride comfort, uh, and then the pitch motion of the vehicle, the roll motion of the vehicle, and so on. Okay, so these are the different aspects that we will be looking at. Okay, so we will derive models to understand or analyze ride comfort, pitch, and roll of the vehicle. Okay, so of course we are going to make certain assumptions. Okay, so in this uh, analysis of vertical dynamics, there are different classes of models that one would be looking at. Okay, so what are the different class of models and what are their applications? Okay, the first one is what is called as a quarter car model. So as the name indicates, if we consider a car, a typical car, it will have 4 suspension units, right, at each wheel assembly. So a quarter car model considers 1/4 of the car, 1/4 of the vehicle, and models what happens to the response at that particular suspension. Okay, so this quarter car model is typically a 2 degree of freedom model, and it is used to study the response of the suspension to the road inputs, okay, the road excitation. So that is the main application of the quarter car model. So we use the quarter car model to study the suspension response to road inputs. So we typically call this as studying the heave motion of the vehicle. Okay, what is heave motion? It's essentially moving in the vertical direction. Okay, so that is what is called as heave motion. Okay, yeah. So that is the quarter car model. Then we have what is called as a half car model. As the name indicates, in the half car model, we consider half the vehicle, right? So it depends on how we visualize the vehicle, half of the vehicle. So this is going to be a 4 degree of freedom model. And what we do is that like it's typically used to study the heave motion and the pitch or the roll motion. Okay, so depending on which half of the vehicle we are considering. So the heave motion and the pitch or roll motion. Okay, so what is pitch? Pitch is essentially rotation of the vehicle about the lateral axis, right? Roll is rotation of the vehicle about the longitudinal axis, right? So in the half car model, we study either the pitch motion and the roll motion in addition to the heave motion. Okay, so then there is something called as a full car model in which we study all the three. Okay, so this is a generic model, uh, and typically it is a 7 degree of freedom model. And what we do is that this can be used to study the heave, pitch, and roll motions. That is the application of the potential application of the full car model. Okay, so these are 3 classes of models which are used. So then the natural question that arises, right? As we know, every model, is used for a purpose, right? Is derived for a purpose and then like used for some analysis, right? So the question, what to say, naturally arises as to what phenomena do we analyze using these models? Okay, so that is an important question that comes about, right? So what do we analyze using these mathematical models? Okay, so we can analyze ride comfort. Okay, so as the name indicates, ride comfort denotes the level of comfort that the occupants of the vehicle have when the vehicle is being driven on rough surfaces, right? So the road surface is not exactly a smooth surface, right? So it is going to have irregularities and roughness. So when the vehicle is driven on this rough road, the question that naturally arises is that like, what is the impact felt by the occupants of the vehicle? And that is what we are essentially going to study under ride comfort. So it is also called as road isolation. Okay, as the name indicates, we want to study how much we are able to isolate the effect of the road irregularities on the occupants of the vehicle, right? So that is one purpose, all right? So then one can essentially also study what is called as a road holding. So what is this phenomenon of road holding? We want to ensure that the tire stays in very good contact with the road, right? So even when the vehicle is moving on a rough surface, right? So why is a good contact with the between the tire and the road important? As we would have already realized by now, all forces, let it be for longitudinal motion, lateral motion, are all transmitted through the tire road interface, right? So, and we have seen that the peak forces are all proportional to the vertical load, right, at the tire road interface. So, under such a scenario, if there is too much variation in the normal load or the normal force of the tire road interface, the vehicle's response will be affected, right? So consequently, uh, we want to minimize the variation in the normal force at the tire road interface. Okay, so that is important. So we wish to minimize the variations in the normal load of the tire interface, and that's what is essentially characterized through road holding. Then we also want to, if you want to study pitch and roll stability, like one could use the corresponding models to study the vehicle response and analyze pitch and roll stability. Okay, so that is also an application of these models. All right. So we will anyway study a few related concepts as we go along. Okay. So now there are, depending on the type of suspension that is used and the characteristics of suspension that is used, like typically vehicles can be classified broadly into two categories. I would say not type of suspension, but rather the characteristics of the suspension which is used. Okay, one is what is called as a loosely sprung vehicle. So a loosely sprung vehicle has a soft suspension. So you would have seen that when we have a soft suspension, we have very good ride comfort. Okay, so the soft suspension provides good ride comfort, but then what happens is that like it essentially obviously has a lot of deflection, and that compromises on road holding. Okay, so the contact between the tire road interface is going to see variations, right? So the moment we use a soft suspension. So a soft suspension, a loosely sprung vehicle that has a soft suspension provides good ride comfort, but then compromises on road holding. Okay, so that is as far as a loosely sprung vehicle is concerned. On the other hand, we also have what is called as a tightly sprung vehicle. So what does a tightly sprung vehicle possess? Typically, a tightly sprung vehicle has a hard suspension. So in other words, it is going to have a stiff suspension spring, or the spring stiffness is going to be pretty high, and consequently, it will result in good road holding. Okay, so it will minimize the variations in the normal force of the tire road interface. That is a positive attribute. But then there is a compromise on ride comfort. I'm sure we'd have experienced this, right? So when we have a hard suspension, the moment the vehicle's wheels go on a pothole or a speed bump, right, we are going to feel that effect on our body. On the other hand, if you have a soft suspension, those disturbances from the road will be attenuated and we'll have good ride comfort, but then there is a compromise on road holding. Okay, so there is always a compromise. Okay, so the question is, how do we sort of like reach a middle ground, right, when we deal with suspensions? Okay, there is always a challenge in suspension design. And there is another classification of suspension based on the type of suspension, or the once again, the variation in suspension parameters that can happen during its operation. The first class is what is called as a passive suspension. A passive suspension has fixed stiffness and damping. So as we know, in a typical suspension unit, the two main elements are going to be the suspension spring and the suspension damper, right? So there is going to be a compliance, there is going to be a stiffness, and there is going to be a dissipation element, right? An energy storage element in the form of a spring, and an energy dissipation element in the form of a shock absorber, right? So those are the two main elements that make up a suspension. So if you take a passive suspension, which is what is mostly found in road vehicles, we will see that we design the suspension considering various trade-offs. We realize the suspension spring and the shock absorber, and we install it in the vehicle. That's it, right? So as time progresses, we will not be able to change the characteristics of the suspension. Okay, so that's a passive suspension. On the other hand, we can have what is called as an active suspension. In an active suspension, what we have is going to be an actuator that can provide a variable force on the masses supported on the suspension, and that can improve the suspension performance. Okay, so obviously it's more complex, but then like it provides better performance, right? So it has an actuator that can provide a time varying force on the suspension, the masses supported by the suspension, and this improves the suspension performance. Okay, so it has an actuator to improve suspension performance. Okay, so that is an active suspension. So somewhere in between is what is called as a semi-active suspension. So what is this semi-active suspension? A semi-active suspension is one wherein we don't have an actuator per se, but then we essentially can include a variable damping element. Okay, so that the energy dissipation or involved in the suspension can be varied to a certain extent, and this can certainly provide better performance when compared to a passive suspension. Okay, so semi-active suspension is somewhere in between. Okay, so obviously a passive suspension is the simplest and least expensive, right? So active suspension is going to be complex and expensive, right? A semi-active suspension is somewhere in between. Okay, so a few more terms before we go to the analysis. So in today's class, I'm just going to set up the definitions and some fundamental concepts associated with vibrations before we go and do suspension analysis and derive the corresponding models. Okay, so another set of definitions that we should be familiar with when we deal with suspension analysis. The first one is what is called as a sprung mass. So typically what happens is that like although the suspension is mounted in the vehicle in various configurations, what we do is that like we visualize the suspension to support a mass above it. Okay. So that is what is called as a sprung mass. So sprung mass is indicative of the vehicle mass supported above the suspension. Okay, so that is the notion of the sprung mass. On the other hand, we have what is called as the unsprung mass, and this is the mass which is supported between the suspension and the road. Okay, so this includes the tire, the wheel rim, the brakes, and so on. Okay, so essentially, the unsprung mass is the vehicle mass between the suspension and the road. Okay, so why does it become important, and how do these definitions affect our analysis? See, if we take a typical IC engine powered road vehicle, right? So we are going to have the most of the powertrain, the engine, the transmission, and so on, right, being part of the sprung mass of the vehicle, right? But if you go to, let's say, electric powertrains, right, with, let's say, hub motor configurations. So what will happen is that like the hub motor will be driving the wheels directly and it will be mounted in the wheel hub. So then what will happen is that like the unstrung mass will increase, right, in such motors when compared to the previous case. So we need to be very aware of the sprung mass and the unsprung mass, and then be careful about like analysis when we are dealing with various vehicle configurations. Okay, so that's why we will be looking at the sprung mass and the unsprung mass concept. Okay, now comes an important question. Okay, so we are going to ask ourselves the question of what is meant by natural frequency and how do we calculate it? Okay, so let us try to answer that question. Okay, so because when we are going to deal with suspension analysis, we are going to deal with like the analysis of the vibrations of the various masses involved in the vehicle, okay, in response to various stimuli from the road. uh, then we need to be aware of like how to calculate the various natural frequencies associated with these vibrations and analyze them. Okay, so that's why we are going to pose this question. So today let's set up the basic theory behind it, and then like we will look at it. Okay, so let us first start with 1 degree of freedom systems. Okay, so let us say we consider the single degree of freedom mass spring damper system. Okay, so we'll start with the simplest system which we can consider for this analysis. Okay, so and as we know, we are going to draw the diagram, a simple schematic for this. So let me draw the schematic for the conventional 1 degree of freedom mass spring damper system. So we have a mass M, which is connected to a spring and a shock absorber or a damper, right? So let us say this is our mass M, and let us say it is connected to a linear spring. This is a spring, and then we have a shock absorber. Okay, yeah. So let's say the spring constant is some K, the damping coefficient is some C. And let us say the displacement of the mass from its equilibrium position is denoted by x of t, and we are applying a force f of t on it. And all of us know the basic governing equation of the system, right? So the governing equation is going to be mx double dot plus cx dot plus kx equals f of t, right? So that is something which all of us are familiar with. So let's write it down. This is going to be mx double dot t plus cx dot plus kx equal to f of t. Okay, so this is the governing equation of this single degree of freedom mass spring damper system. So all of us know the formula for the natural frequency. So this natural frequency, the formula for the natural frequency, omega n, is going to be equal to square root of k by m. Okay, so we are all aware of this formula. The question is how, right? How did we go from this equation to this formula, right? For the natural frequency of this single degree of freedom mass spring damper system. Okay. So any answers about that? No. Any idea as to how we
So we will compare this equation with our vibration equation.
We will compare this equation with our vibration equation. Is it okay? Fine. Any? Can you expand a little bit on that? What do you mean by that vibration equation? No.
Sir, actually, we'll have to take Laplace on both sides, and from the transfer function we get it, we will have to see which variable has this root of k by m.
Which root has this variable k by m? Is it okay? Fine.
Yeah.
Okay. All right. Okay. Any other thoughts on how we went from this point to the equation to the what to say formula for the natural frequency, which is square root of k by m?
So this x dot t will be compared with 2 zeta omega n. And here it will be c by m.
Okay. So I think these are all like nice answers, right? So you are essentially saying that, look, I will compare it with, like the standard forms, right? Yeah. Okay. And then like I would essentially interpret and then like sort of like say this is my formula for the natural frequency. Okay. So that's a nice way of interpreting it. But then like we are going to figure out a general way. The reason we want to essentially look at the generic method is because see whatever we are discussing is fine for a 1 degree of freedom system, right? But then when we go for a multi-degree of freedom system, right, which we are going to encounter as we go further in our discussion on, the models, suspension models that we are going to look at. So we will see that we will have more degrees of freedom. Then the question becomes, how will we come up with the expressions for the natural frequency, right? So in order to figure those things out, it is important to understand how we got here, all right? So for that, let's define the natural frequency. So what is natural frequency? So the natural frequency of any system, right? So not only this 1 degree of freedom system, right, is the frequency at which the mass would oscillate given a perturbation, would oscillate subject to a perturbation given an undamped and unforced system. So what do we mean by this? So this is the definition of natural frequency. Okay, so if you want to visualize natural frequency, so that's why we would have typically considered a mass and a spring, right? We will say, hey, look, just pull the mass and leave it, it will keep on oscillating forever with the natural frequency, right? So that's the definition of natural frequency. So let's say we remove damping, right? And then like we essentially remove the external force F of t. We just displace the mass m, from its initial state by a small amount and then leave it. So it will keep on oscillating, right? That's what is called simple harmonic motion, right? So essentially it will keep on oscillating forever, and that frequency is what is called as the natural frequency. Okay, so that's how it is defined. So let us now apply this definition in this case. Okay, so and then like we will see what happens. So let us consider, oops, there's some issue, 1 minute, sorry about that. Okay, yeah, so let us consider the unforced and undamped system, right? So corresponding to the above equation. So let's consider the undamped and unforced system corresponding to the above equation. So undamped means Cx dot becomes 0, right? Unforced means right hand side becomes 0. So what are we left with? We are only left with mx double dot t plus kx t equal to 0. Okay, so that's what we are left with. Now, this is a second order linear ODE, right? It's a second order. So if you look at this is a second order linear homogeneous ODE. Why am I calling it homogeneous? Because there is no forcing term or forcing function, right? On the right hand side. Okay, so that's why it's called as a homogeneous ODE. Okay, now the solution to this equation is the following. What is the general form of solution to this equation? Not only this, for linear ODEs with constant coefficients, typically the solution is in the form of exponentials. So essentially, the solution is of the form some x naught e power nt. How do we know this? Okay, so anyway, I'm not going to go into the mathematics. For see, whenever we are given like any mathematical equation, right? So we are always interested in two aspects. Okay, so when we are given a mathematical equation, we are interested in existence of solutions. So the first question we ask ourselves is that, like, for the equations that we are given, does a solution exist? Okay, once we figure that one out, once we determine that a solution exists, so whether the solution that is obtained, is it unique? Okay, so those are two important questions which we'll ask whenever we deal with the mathematical equation. And it so turns out that for linear ordinary differential equations with constant coefficients, a solution exists, and the only solution is the exponential solution. Okay, so that is why we essentially look at solutions of the form e power nt. Okay, I hope it's clear why suddenly, like in many references we would have seen, okay, this let the solution of this equation be some c1 e power n1t plus c2 e power n2t. Okay, that is because of this general result. Okay, so if we have a linear ODE with constant coefficients, so it has been proven that the solution to that equation is unique, and that solution is the exponential solution. Okay, so that has been proven. Okay, so consequently, what happens is the following. Okay, so if we substitute this solution into this equation, so we have m times, what will happen to x double dot? We will get n squared x0 e power nt. Why? Because if we differentiate e power nt with respect to time, we get n e power nt, right? and then we differentiated once again, we get n squared e power nt. Okay, I hope it is clear how we got n squared x naught e power nt. X naught is anyway a constant, right? So that's why we get this. Then plus k times x naught e power nt is equal to 0. Okay, so then if we simplify this equation, what we are going to get is the following. You'll get m times n squared plus k x of 0 e power nt is equal to 0. Okay, so now if you look at this equation, there are three terms: m n squared plus k, x of 0, and e power nt. So there are three terms, and the product of these three terms is 0. So when the product of three terms is 0, one can be 0, two can be 0, or all three can be 0. Okay, so let's argue which one is 0 and which one is not. Certainly x0 is not equal to 0. Why? Because if x0 is 0, then we don't have any solution to begin with, right? So x0 comes as a multiple in the solution, right? It multiplies e power nt. If x0 is 0, we get the trivial solution. So we are not interested in that. E power nt is also not equal to 0 for all t. Yes, it may. It may ultimately go to 0 if n is having a negative real part, right? So it will decay to 0. But however, e power nt is not going to be 0 for all t. Okay, so that's something which we can readily realize. So from this argument, what can we say? We can only say that m times n squared plus k is equal to 0. This implies that the coefficient or the exponent n is going to be equal to square root of j k by m. Okay, so I hope that is clear to all of us, right? How we got square root of j times square root of k by m. Okay, because m times n squared plus k equals 0 means what will happen? N squared will be minus k by m, right? And we take the square root of it, we get a complex index, right? So that's what we'll have. Okay, so I hope it is clear how we got this. All right. So any questions till this step before we go ahead? We have a couple of more steps before we come to the answer. I hope till here it's clear, right? So we have used the definition of the natural frequency to look at the undamped and the unforced system, and that equation is mx double dot plus kx equals 0. And then like we know that from the theory of ordinary differential equations that the only solution to this class of equations is of the form x naught e power nt. Okay, so that's what we have done. We have used, we substitute that, and then like we get this exponent n to be plus or minus j times square root of k by m. So this will give us the solution x of t to be equal to x0 in general for this problem, e power plus or minus j square root of k by m t. Okay, so this is what we'll have. And from here we can immediately realize, right, why we call we get the natural frequency as square root of k by m. Why is that? Because we can see that this is an exponent with a pure imaginary exponential term with a pure imaginary exponent, right? And from the so-called Euler's relation, so we can immediately see that e power j omega t consists of cos and sine, okay? Cos omega t plus j sin omega t, and e power minus j omega t is anyway going to be cos omega t minus j sin omega t. So we can see that the solution is going to be an oscillatory solution, right? And the frequency of oscillations is going to be square root of k by m. So the solution x of t is going to be oscillatory in nature. With a frequency of square root of K by M. So this implies that the natural frequency omega n is square root of K by M, right? I hope it is clear how we got this expression for a single degree of freedom system. Okay, so I hope the entire discussion was clear, right? So we consider the single degree of freedom mass spring damper system. We apply the definition of the natural frequency as the frequency at which the system will oscillate when it is undamped and unforced, and but subjected to a perturbation. And then like we derive this expression, right, as omega n to be square root of K by M. I'm going to pose a question to you. Please think through and then like try to look at the answer. But we will discuss it, right, when we go to multi-degree of freedom system, right? How do we calculate the natural frequencies of a multi-degree of freedom system? Okay, so that is a question that we need to ask ourselves going forward. Okay, I think we will answer that question as we do the quarter chord model and the half chord model analysis, which will be multi-degree of freedom models. All right. Okay. So any questions on what we have done today? You know, like as far as the discussion on the natural frequency definition and derivation is concerned? Okay, so I'm going to do the quarter chord model and the ride analysis in the next class, so that like we will be able to concentrate on it for the entire class. In the remaining time, I want to revisit the problem that we considered in the previous class as to how do we get the gear ratios if we have, let's say, a 5-speed or a 6-speed gearbox, right? So for that, I want to pose a question for the data given, right, in the problem yesterday. You know, like design a 5-speed gearbox. So what do I mean by the data given? You know, like we discussed a homework problem, right? So where I had given, you know, like data on the engine and the requirements of gradability, the maximum speed, and so on, right? All of the parameters that are required. So now the task is to design a 5-speed gearbox, right? So the question is, how do we design that, right? So now, when n is equal to 5, please remember what are all the parameters that we need to calculate. We need to calculate NT1, NT2, and NT3, NT4, NT5, and ND. Okay, so these are the 6 parameters that we need to calculate. Okay, so we are given that the 4th gear is a direct drive. Let us say that's a usual convention. Let's say we know that NT4 is equal to 1. Okay, so that is given to us. So now the question is, how do we determine the other gear ratios? Okay, so I'll explain what the problem is so that like you can also think of solutions and how to address them. Okay, so if we recall from the discussion on transmission matching, a condition on gradability is typically used to derive an expression for the first gear, right? So if you look at the equation for gradability, so let's say engine maximum torque is Te max, we multiply it by the first gear ratio NT1, and then we multiply it by the final drive ratio ND, and then multiply it by the transmission efficiency, divide the entire product by the wheel radius R, that's going to be equal to the loads which the vehicle, the powertrain has to overcome when driving on a grade, which we predominantly the grade resistance, but then we also have the rolling resistance term, right? So that's the equation for NT1. right? And as we discussed, the highest gear ratio is obtained through specifying the maximum vehicle speed, and then like we get an equation to relate that, right? So let's say omega E1 is the corresponding engine speed. We have omega E1 R times 1 minus I divided by NT5 ND. That's going to be equal to V max, okay, which is the maximum longitudinal speed of the vehicle. Now, what is the challenge here? You can observe that there are two equations, but then three unknowns. What are the three unknowns? NT1, NT5, and ND. Okay, so previously when we had a 4-speed gearbox, we take NT4 to be 1, and immediately we can get ND from the equation for maximum vehicle speed, and then we substitute that ND in the equation for gradability and we can get NT1, right? So pretty straightforward. But now we have 5 gears and we are given that the 4th gear is a direct drive. So consequently NT4 is 1. But then if you look at these two equations, we don't have NT4, right? We have NT5, ND, and NT1. So we seem to be stuck. So what can we do? So what do you think we can do to solve this problem?
Sir, we need to fix NT5.
We need to fix NT5, is it? Okay. How do we do that?
Or we'll have to fix ND.
Okay. So, but then see, the task is to calculate those parameters, right? So we need to find the numerical values of those parameters, right? Is it not? Okay. So if you mention we can fix those values, like how can we go about it? Any ideas?
Sir,
So,
we know the geometric progression ratio between the gears, right? So from that 4th gear, we can calculate the NT5 with the ratios available, right?
oh, but yes, okay, that's a good thought. But then, like, we have to calculate the geometric progression ratio, is it not? So let me write down based on what you have said, right? See, the geometric progression ratio, K subscript G, is going to be equal to the ratio of two successive gears, right? NT2 by NT1, NT3 by NT2, NT4 divided by NT3, right? And NT5 by NT4. Okay, so that's what we have in this particular problem, right? When you have 4 gears, right? Is it not? Now, anyway, we don't know K subscript G, right? If we knew K subscript G, we can immediately calculate other gear ratios. Why? Because we know NT4 to be 1. And then it's only a matter of substituting K subscript G and then like getting the other gear ratios, right? But the challenge here is that like we don't know K subscript G also, right? Okay, good thought process, but then how do I get K subscript G? Okay. I hope my question is clear, right? So, yeah, if
Yes,
we
sir.
knew K subscript G, we can immediately get NT3, NT5, NT2, and NT1, right? So, but we don't know that. And that is your hint, okay? Because we can see that we have 2 equations and 3 unknowns. But do we really have that, or can I do something using this geometric progression equation along with the previous 2 equations and then like solve the problem? Okay, so I would suggest that you please think about it, okay, and then like try to come up with a solution. All right, so please let me know in the next class as to how we can solve this problem. I hope the problem statement is clear. So similarly, one could extend the same problem statement to 6 gears and so on, right? So we just need to ensure that we are able to calculate these first get gear ratios using these equations. Okay. All right. Any questions on this? All right. Okay, so if not, I think I will stop the lecture for today here. In the next class, we will get started with the quarter card model that is typically used for ride analysis. And then we will derive the equations of motion and do the analysis of the quarter card model. Okay, so thank you for attending today's class.